Hi everyone. So in this video, I will run you through problem 13.29. This is a very lovely problem and it's a good one to work through to prepare yourselves for an exam or a test. So when we look at this circuit, we will see that there is a 450 volt source that is powering this circuit. We have a switch that has been in position A for a very long time, and at time t equals 0 we move the switch to position B. So this problem asks firstly to construct an S domain circuit for t greater than 0, and we need to find the voltage V1. It is this one that is over the 25 ohm resistor, and then the other last question is to find V2, which is the voltage that we measure in this parallel combination of capacitors. So we need to construct an S domain equivalent circuit for time t greater than 0, but the switch has been in position A for a long time before it moves to position B. So because it has been in position A for a very long time, we will notice the following. We have a 10 microfarad capacitor, and we have a 16 microfarad and a 24 microfarad here. So this means that this 450 volt source has charged these capacitors. So therefore we have some initial conditions to deal with. So if you remember that according to this diagram, that if we have initial conditions, our capacitor in the S domain will have some other form like this, and we have some or other voltage source that we have here, and we need to include this when we want to draw our S domain equivalent circuit. So before we continue with this, we first need to figure out what is this initial conditions so that we can find what these sources would be that is in series with the capacitor. So for our first analysis, we will only consider this loop. So we will only see what happens to the capacitor, the 10 microfarad capacitor, the 16 and the 24, and then the switch moves to position B. So then we will look at what happens here, because our S domain circuit will deal with the three capacitors with their sources that we're going to figure out now, and then we have an inductor and we have our resistor. Remember, since there is no current that flows initially through the inductor, there is no initial condition for the inductor. So let us see. So I redraw the circuit, and we are going to look at the following few things. Firstly, we need to recap on what the capacitors in series looks like. If we need to determine the equivalent capacitance. Why do we need to do that? Because we have in our circuit these guys over here, and then it is also, so that is why we're going to look at the parallel ones, and then they are in series with the 10 microfarad. So the way to calculate the equivalent capacitance, if we have a series combination of caps like here, is it is 1 over C1 plus 1 over C2, and then we get the reciprocal of that. Then capacitors in parallel is we just add them as they are. So for the 16 microfarad and the 24 microfarad in parallel, we get is just 16 plus 24, that equals 40 microfarad capacitor. So that is what we're going to get if we add these in parallel. Then a new thing to introduce is the concept of the charge in a capacitor. Why is that important? You see, since we are going to construct the S domain equivalent circuit, we will see that these capacitors, like the 10 microfarad and this parallel combination of 40 microfarads, each stores a different amount of charge. And because of that, there is a different voltage that is over it. So to determine what the sources would be in the S domain for the 10 microfarad, we need to calculate that. And also for the parallel combination, it's also different. But the total voltage, that when we look at all these capacitors, like if we add this one, the 10 microfarad, and this 40 microfarad one in series, then that would charge to the 450 volts. But since we're going to determine the voltage V2, we need to make sure what is the initial voltage that this parallel combination is charged to. So therefore, to determine that, one of the easier ways is we can determine what is the charge or the coulomb that is in the total circuit, and then given the capacitance, we can find the voltage that is over the capacitors. That is one way. The other way that I've written here in the red is we can make use of the voltage division equation. But we have different ways in determining the voltage using voltage division, whether we have a resistive circuit or whether we have a capacitive circuit. So let's have a look. So here I've written down 3 voltage division circuits. So firstly, we have resistors, a resistive circuit, then we have a capacitive circuit, and then we have an inductive circuit. So the beautiful thing here is that you will note that the way you approach this is the same. But when we take a look at the capacitors, we will see that the equations differ a little. Let us review what happens in the resistive circuit. So we have a resistor, in this case R1 and R2. So I'm not going to do the mathematical process followed to get to the equation here below. I'm just going to tell you how to use it. So we have if we want to find the voltage V0, that is equal to this resistor R2 divided by the series combination of these two times the input voltage. Then we find V0. But when we take a look at the capacitors, now what happens here is if we want to determine the voltage V0 that we measure over the second capacitor, to do that is we follow this equation. We take the first cap, C1, divided by the series combination of the two times V1. Okay? Then remember, since we work in the S domain, I wrote down it is C1 and C2, but remember we work with the impedances. So the impedance ZC1, and here's the impedance of ZC2. So we have the impedance of ZC1 over the impedance of ZC1 plus ZC2. And now when we go to the inductors, since in the S domain, the impedance of the inductor 1 and the impedance of the inductor 2. So it follows the same approach as the resistors. So to find the voltage V0, which is over the second inductor, it is the impedance of the second inductor divided by the series combination of the two. Remember, if we go to the capacitor, since we work with the impedance, we do not need to add these capacitors in a weird way. Okay, so let us continue. So here's a quick example of how to determine the voltage over these capacitors. And so just to show you what happens, and something very interesting. So firstly, if we note, we have the impedance of the capacitor, and that is equal to 1 over j omega c. So what this tells us is that we have the capacitance, and we have the frequency omega. So in the S domain, that j omega will be replaced with an S. So according to Ohm's law, we have that the voltage is equal to the current times the impedance. And we're later going to look at this equation where we need to determine the charge. But firstly, for example 1, we have an input voltage V1. So here is V1. And it is somewhat other oscillating cosine wave, sinusoidal, with an amplitude of 10. And we have a frequency of 80 Hertz. And we have no phase offset there. So there is plus 0. So we can determine the impedance for capacitor C1. And for the impedance for capacitor C1, we have 1 over J 2 pi times the frequency times C. And we let C be equal to, in this case, 10 microfarads. Okay. Then that is equal to 20 ohm. Capacitor C2, we have the same equation, but remember C in this case is 22 microfarads, so we have 90 ohm. So what you see here is the bigger capacitor has a smaller impedance, where this smaller capacitor has a bigger impedance. So what happens according to Ohm's law is the voltage drop is equal to the current times the impedance. So if a bigger capacitor is used, therefore the impedance is lower, and that means that the voltage drop will be lower. Okay, so let us get the equivalent impedance of the circuit. So that is equal to 200 plus 90 gives us 290. So we just added these two impedances in series, and therefore we have the total impedance for the circuit. So if we want to find the current, there is a current I that flows through these capacitors. According to Ohm's law, VI is equal to the voltage divided over Z equivalent. That is 10 divided by 290. So we have 34.5 milliamps. Okay, so now we have the total current, and therefore we can find the voltage drop that is over both of these capacitors. So let's have a look. So the voltage drop is then as follows. So the voltage over C1 is equal to the current I times the impedance. Remember, the impedance of C1 is the smaller capacitor. So following Ohm's law, we have a 6.9 volt drop. For VC2, we say we have the current I times ZC2, and remember that is the 22 microfarad cap, so that's a bigger one. Follow the equation, we have a 3.1 volt drop. So from this, you will see that the smaller value capacitor will charge itself more than the higher voltage capacitor. Okay, so a smaller value capacitor will charge itself to a higher voltage, and a larger valued cap will have the smaller voltage drop. Okay, now let's look at the second method of determining the same voltage. So in this instance, we make use of the charge equation, which says that the total charge in the circuit is equal to the total capacitance times the input voltage. So remember from the previous slides that to get the equivalent capacitance for series capacitors is the reciprocal of the inverted sum. Okay, so if we add 1 over C1 plus 1 over C2, and we get the inverse of that, we have 6.875 microfarads. So that is the total capacitance of the circuit. So we can follow this equation of the total capacitance we use here in the charge equation. So you find that the total charge that has been stored in the capacitors in this total circuit is 6 times this 6.875 microfarad times 10 volt, and that is equal to 6.875 times 10 to the power minus 5 coulomb charge. So now we can find the voltage VC1 is the charge that we have, the total charge of these two capacitors, divided by the capacitance C1. So that equals 6.875 volts. So therefore you can already see that the 10 microfarad capacitor, the smaller one, has a big voltage drop across it. So to find the voltage over the other capacitor, the 22 microfarad one, you can either just do a 10 minus 6.875, that is equal to 3.125 volts. There we have it. But just to show you, for the sake of being complete, how to use the charge equation, you'll see that VC2 equals Q divided by C2, that is equal to 3.125 volts. See, that's pretty awesome. So lastly, just to illustrate to you why we can use the voltage division equation that was on the second slide, is let's see. So here we have that same circuit, and let's use the voltage division equation where VC1 is equal to the second capacitor divided by the sum of the two times the voltage. So if we want to get VC1, it is the C2 divided by 10 plus 22 microfarad times the input voltage is 10 volt, and that is equal to 6.875, exactly the same. And if we want to find VC2, that is equal to C1 divided by C1 plus C2 times the voltage V0, and that is equal to 3.125 volts. So you see, the voltage division equation is basically just splitting the input voltage that we have according to a certain ratio. And because we're working with relationships, we do not need to worry about all the units of measure or the impedance, whatever. We just split that voltage according to this ratio. So therefore, this is all the ways that you can do it. So let us go back to our problem. So here we have that same circuit in the beginning, but when we look at the circuit for time t less than 0, for when the switch was in, I'm just going to write it, for the switch in position A, we need to look at that because we need to find the initial conditions. So our circuit would look something like this. We have a 450 volt source, and then we have our 50 kilo ohm resistor, and we have our two capacitors. You see we have a 10 microfarad and a 40. Okay, so because in this circuit the capacitors, they charge, so therefore they will draw a lot of current until these two capacitors are charged to have the same volts as the source. So therefore these two will have 450 volt that has been stored over there. But that 450 volts is divided according to the charge that each capacitor stores. So we can just use that voltage division for capacitor equation to find that the 10 microfarad capacitor has a 360 volt static voltage drop, and we can see that the 40 microfarad cap has a 90 volt source, and that we can include in the estimate. And so these are initial conditions. 10 microfarad cap is 360 volts, and a 40 microfarad has a 90 volt. You can see you're correct. If this smaller capacitance has the bigger source. Okay, so now we can draw the S domain equivalent circuit. So here's our S domain equivalent circuit for time t greater than 0 for when the switch is switched to position B. So you will see that we have, let me just go for a moment back to our previous circuit. So you see we have on this side on the left, let me just get another clear, we have a capacitor, we have these capacitors, and each of them will have their sources, we have an inductor and this resistor. So now we draw that, you see here we have our resistor, our inductor, then we have our capacitor, here's the 10 microfarad cap, here's the 40 microfarad capacitor, and with their sources respectively, the 360 and the 90, the S domain. So just to show you where I got that 25 times 10 to the power of 3 over S for the capacitor's impedance is, remember that this is equal to 1 over SC. So we have 1 divided by S times 40 microfarad, and that is equal to 25,000 over S. Okay, so this is where we got this value. So next, our initial question was to draw, number 1, the S domain circuit. So we've already done that, so that is completed. So secondly, the question was we need to find the voltage V1 and then V1T. So to do this, we have a very simple equation to follow. We can treat this problem like a voltage division problem. You see, where the voltage V1 is the voltage that we find over this resistor. So to find V1, we do voltage division equation. So that would be equal to the following. Okay, so we have our R value, which is 25 ohms, times our input source, and it is 360 plus 90, so that is 450 over S divided by the sum of all the impedances, so that is plus 25 plus 1.25 times 10 to the power minus 3 S plus the combination of the capacitors, and that is 100, it is 125,000 over S. Okay, so if we add this impedance with this one, we get 125,000. If we just simplify this equation, you will find that we have 9 times 10 to the power 6 divided by S plus 10,000 squared. So to find V1 of t, we just do the inverse Laplace transform of V1s. You can see firstly through inspection that we have a squared value. So if you remember that the Laplace transform of t to the n, so that is what we see there, so there must be some other term of t. Then we have a constant here, and we have some other exponential function here, so we can just apply that. So for our second problem, let me just clear that up. Okay, so the second question was we need to find the voltage V2. So the voltage V2 was the voltage, if we go back, over here. Okay, So to find that voltage over the capacitors that we have there is we follow the same approach as previously. We treat this as a second voltage division problem where we have the impedance 25,000 and we have the impedance of the capacitor, and then the initial sources is 450 over S divided by the sum of all the impedances. But remember, since we have a 90 over S, that source over there, we just need to subtract that so that we can find the voltage that is over the capacitors. So let me just go back again. So you see V2 is the voltage over the capacitors. So whatever we find the voltage to be, we just subtract the 90 over S. Okay, so let us do that. So V2 is equal to, let us see, we have the source 90 over S, that is what we have, and we subtract the voltage over these two capacitors, and that is again voltage division. So that voltage over that capacitor is 25 times 10 to the power of 3 over S divided by the sum of all these impedances. So it is again 125,000 over S plus 25 plus 1.25 times 10 to the power minus 3S, and that needs to be multiplied by the 450 over S. So when we simplify, we have something like this: S plus 20,000 divided by an S squared plus 20,000 S plus 10 to the power of 8. Okay, so that is V of S. So to find V2 for T, we just do the inverse Laplace transform of this one. So we need to perform partial fraction expansion. Okay, and that's that. So this is how you would follow example of problem 13.29. So I hope this helps you to understand this problem. So yeah, see you in the next video.